In this video, we're going to be talking about Torricelli's theorem. So Torricelli's theorem is V is equal to the root of 2gh, which describes the exit speed of water as it exits out the valve of a tank at a h that is below the surface water level, and it is a special case of Bernoulli. Now, let's look at it in action. Our setup is going to be when we have a tank and when the water is coming out a point below the surface, it is going to be in free fall, and it is going to act as projectile motion as it launches from here, which is the y max point for it, and it is going to have a vy here of 0, and then it is going to fall like this, which will allow us to use kinematics. So when do we use this? We are going to use this when our fluid is incompressible, non-viscous, the V at the surface is approximately 0, and you are going to have a liquid. Now, when would you not use this? You wouldn't use this when your surface pressure is not equal to about the pressure atmospheric. And you don't use this for gases or when you have multiple different types of fluids inside of your tank. And when your V surface is not approximately 0. So when it's not negligible, when there's an apparent V that is different at the surface. And also when you have energy loss, like friction or viscosity. And the reason why we can say that P atmospheric is P surface is because we can see that the water is going to exit into the atmosphere. And the atmosphere is just so large so that that pressure is just going to overtake. So we can see that here the water is going to exit out into the atmosphere, which is why we'll say we'll have P atmosphere at this point. And also when you're at the top here at the surface. So this is the hole. Now let's do a derivation. So you are going to have a hole opening in your tank that is exposed to atmospheric pressure. So you're going to have two sides of your equation. So one side is going to be your top surface, and then one side is going to represent your hole. So your general equation on your formula sheet looks like this, but you don't leave it just like this. You have to basically identify what is going to be what for each of these variables in the situation that you're given. So in our situation, we can identify that P1 is equal to atmospheric pressure and P2 is also equal to atmospheric pressure. And this is great because this is going to let us cancel that out. And we were given that our V1 is going to be approximately 0, which is the surface speed, the velocity at the top. That's approximately 0. So then if we plug in that V1 is equal to 0 here, and that pressure 1 here, pressure 2 here, that is how we are going to get these things to cancel out. So P atmospheric cancels out on both sides, and that 0 squared is going to make that cancel out. So we're left with rho gy1 is equal to 1/2 rho v2 squared plus rho gy2. So then you can just take what you have here, you can divide both sides by rho, and then you can multiply both sides by 2 to cancel out that 1/2. Then you're going to take the root of both sides, and then you get V is equal to the root of 2gh. Our special case is when we're going to have pressure that is not equal to atmospheric pressure, which is going to be our special case. So V is equal to the root of 2P1 minus P2 divided by rho plus 2gh. Now let's do some practice problems. Let's say we have a large tank filled with water, has a small hole located 2 meters below the surface. So the tank is open to the atmosphere. What is the speed of the water exiting the hole? Now, if this is 2 meters below, we have our water exiting here. We can find this by just applying our formula. So we get approximately 6.3 meters per second, which is option C. A tank has 2 holes, one at depth h and another at depth 4h. How does the speed of the water exiting at the deeper hole compare to this shallow hole? So here we have h, and then lower than that by 4 times, we'll say that, okay, this is H, and then this is going to be 4H. So you're going to have water exiting here, and you're going to have water exiting here. Now, we want to find these speeds. So V is equal to the root of 2GH. Now, we're talking about 4H, though, so you're just going to substitute 4H in instead of H. So 4 you can take out, and that's just 2. And then you have 2GH here. So then this is the V shallow that you get. Now, what is the ratio of V deep over V shallow? This is going to be 2, because the only thing that's differentiating these two is that this has a factor scale of 2. And we see that velocity is going to square with the square root of depth anyways in the equation. So quadrupling, so if you quadruple your depth, that is going to make you double your speed. Now, a tank is filled with water to height H. A hole is located at H divided by 4 above the bottom. What is the exit speed of the water? So we have water up to this point H. And then at H over 4 to the bottom, so 1/4 of that way to the bottom, we have a hole right here. And we want to find V. So we have to find our effective height. This is going to be H minus H over 4, which is equal to 3H over 4. So V is equal to the root of 2G, 3H over 4, which is equal to root 3 over 2 GH, because we have 3H here. And we can see for our next problem, we're going to have a tank. Okay, so for this question, this was option B, by the way. So for this question, a tank is pressurized so that the pressure at the surface is greater than the atmospheric pressure compared to an identical open tank. So the speed of the fluid exiting at a hole at the same depth will be what? So our generalized equation we saw earlier is this. So what you see is that if you increase your pressure at your surface, that is going to result in a larger pressure difference, which is going to result in a larger velocity. Because if you increase your pressure, that is going to add energy. And what that does is it's going to increase your V exit. So what will happen is you will have a larger speed of fluid exiting a hole at the same depth. Now for our next question, we have 2 immiscible fluids. On the top, we are going to have oil. At the bottom, you have water, and a hole is located at the bottom of the tank. So here. Down here is your oil. Up here will be your water. So the immiscible means non-mixing. What's going to happen is that when you have your oil, right, your oil is going to contribute rho initial GH initial, and then water is going to be rho water GH of water. So then because we have a moving fluid, you're going to divide by rho water. So V is equal to the root of 2 over rho water times rho initial GH initial plus rho water GH of water. And here V is equal to the root of 2G times rho initial over rho water H initial plus H of the water. And we can see that the pressure contributes from both of our fluids, but the kinetic energy is overall going to depend on the density of our moving fluid. So here we are going to have B, which is what we got right here. Something you need to understand is that H is the vertical distance from the fluid surface down to the hole. It's not the height of the projectile. H is not going to be the y max of your projectile. Because what we're measuring essentially is when you have your tank and you have your water here, right? Our water, in order to reach the hole and then go out, is going down this distance. We're not going down this distance necessarily. That is something else. That's just the projectile's maximum height. So when you plug into Torricelli, this H is actually going to be the H that is in your 2gh root of that formula. So for example, in this problem, let's say that the depth below the surface is going to be 10, and let's say that we have 7 as the height from the hole, and we can say that the hole is 3 meters above the bottom. So let's say make this 3, and then let's make this 7. It's not drawn to scale, but H would be equal to 10 minus 3 equals to 7 meters. So then that would be what you plugged into the equation, 2g times 7, not the 3. So this would be our answer. So you always are going to have your change in y is equal to your surface height minus your hole height, because that's what your change in energy is going to depend on. You always are looking at the surface to the hole. That is your critical reason, because you have to understand that the fluid is going to fall from the surface to the hole, not from the floor up to the hole.